Okay, so in this video, we are going to consider an example of the subspace theorem. So consider the following problem. So we'll choose a vector u and say R4. And suppose we take the vector 1, -3, 2, 4. So we have a vector with 4 coordinates, therefore this is a vector in R4. And we'll take the following set. Say W, and we will take the vectors in R4, so call them X, and we will take only the vectors in R4 that are perpendicular to the vector u. And again, remember your notation of set theory. So here we're saying that the elements in the set W are vectors in R4, so vectors with 4 coordinates. And after the colons, this is the condition. We only take the vectors in R4 that are perpendicular to the fixed vector u. And we're going to try and prove that this is actually a vector space. Well, to use the subspace theorem, the first thing is to actually find a larger vector space that contains our set W. Well, as all the vectors in W are vectors in R4, clearly we have a subset of R4. R4 is a known vector space because we know that Rn for any positive integer n is a vector space. So this will be here our large vector space. And again, the operation of addition and scalar multiplication are the standard ones. So because W is a subset of a known vector space, to prove that W is a vector space itself, we do not have to prove that W satisfies all of the 10 axioms, only the 2 closure axioms. So closure under addition and closure under scalar multiplication. Before we do so, let's just think of the condition in a slightly different way. Vectors are perpendicular if and only if their dot product is equal to 0. So saying that vector x is orthogonal to vector u is the same as saying that the dot product between vector x and vector u is equal to 0. And so we'll go with this condition, which is equivalent to this one. So let's prove the 2 closure axioms and start with closure under addition. And again, the name gives it away. We have to show that the set W is closed under addition. So if we take any 2 vectors in W, we want to show that the sum is still a vector in W. So here's what we take. We take 2 vectors in W. We could call them vectors x and y. So take vector x and vector y in W. Well, we know that because both vectors are in W by assumption, they both must satisfy the condition of the space W, which is that the vectors in W are perpendicular to vector u, and so the dot product between every vector in W and the fixed vector u must be equal to 0. So we know that x.w is 0, x.u, is 0. But vector y is also by assumption a vector in W. And so it must also be perpendicular to vector u. So y dotted with vector u must also be equal to 0. So this is our assumption. We take 2 vectors in W, but vectors in W are orthogonal to u. Therefore, their dot product with u must be equal to 0. What do we want to show? Well, we want to show that if we add these 2 vectors, x plus y, the resulting vector will still be inside the space. So if we take x, vector x plus vector y, we have a new vector. And because the space, at least hopefully, is closed under addition, when we take two vectors from the space W and we add them together, the new vector still is inside of our space. Well, so let's prove this, knowing that by assumption, x and y are vectors in W. Well, what are the vectors in W? They're vectors in R4. Well, will x plus y be a vector in R4? Well, this is obvious, right? If x is a vector in R4, y is a vector in R4, when you add them up, the resulting vector is still in R4. So this is obvious. But we have to prove that for this vector to lie in W, it must be perpendicular to vector u. Well, as we have just said, vectors are perpendicular if they have a zero dot product. So we are going to dot vector x plus y with vector u. Properties of the dot product we can distribute to have x dotted with u plus y dotted with u. By assumption, both x and y were orthogonal to u, and so x dot u is equal to 0, plus y dot u is equal to 0, therefore the sum is 0. So we dotted x plus y with u, the result is 0, therefore our conclusion is that vector x plus y is indeed orthogonal to vector u. Well, because the vector x plus y was a vector in R4 that is orthogonal to vector u, it must be a vector in W. And we now have closure under addition. We prove that if we take two vectors in W, we add them up, the resulting vector x plus y is still inside of our space. And now we have closure under addition. Let us now prove the other closure axiom, closure under scalar multiplication. And once again, the name gives it away. So what do we take in this case? We take a vector in W, say x. So x is in W, therefore x is perpendicular to u, therefore x dotted with u is equal to 0. But it's called scalar multiplication, so we take, of course, an arbitrary scalar. So k is some arbitrary real number. And what do we want to show? Well, that the space is closed under scalar multiplication. So if we do take an element of our space and multiply this vector by any scalar k, the resulting element is still inside of the space W. Well, if x is a vector in W, x is a vector in R4, and clearly any multiple of a vector in R4 is also a vector in R4. So clearly the vector kx is in R4, but we have to show that it is perpendicular to u. Well, let's consider therefore the dot product between kx and vector u. Properties of the dot product, we can factor k outside. This is the same as k times x dotted with u. But by assumption, x dot u is 0. So we have k times 0. Any real number times 0 equals 0. Therefore, the dot product between kx and u is equal to 0, which proves that vectors kx and u are orthogonal to each other. Since vector kx is orthogonal to u, the conclusion must be that kx is indeed a vector in W. And we have proved closure under scalar multiplication. We took an arbitrary vector in our space, an arbitrary scalar, and proved that k times x is still a vector in the space. So the space is indeed closed under scalar multiplication. So, because we have closure under addition and scalar multiplication for W, and W is a subset of a known vector space, by the subspace theorem, W is also a vector space. and it's our conclusion. So W is a smaller vector space living in the larger vector space R4. Now this completes our proof that W is a vector space by the subspace theorem. Now let's just find a basis of our vector space. We know that this is a vector space. Let's find a basis for it and its dimension. And as always, whenever you look for a basis of a vector space, you have to describe the elements of the space explicitly. So let's just rewrite what we have. We have the vector u, which is the vector 1, negative 3, 2, 4. And our space W was the set of all vectors in R4 so that the vector xn W was, the vectors were perpendicular. Of course, that's the same as saying that x dotted with u is equal to 0. So you see what we have here is an implicit description of the elements. We are saying the vectors in W are the vectors in R4 that satisfy this equation. Well, in order to find a basis, we must describe the elements in the space explicitly, so we have to solve this equation. So the vectors that we are looking for are vectors in R4, so they have 4 components. What are they? We don't know, so we label them as variables. And you see the components of the vector must be a solution to this equation. Well, what is this equation? Let's dot x with u. And so we'll get 1 times x1, so simply x1. So this is a vector assuming that it is in W. So vector x dotted with u must be 0. So x1 times 1 plus x2 times negative 3, so negative 3 x2 plus x3 dotted with 2 plus 2x3 plus x4 times 4 plus 4x4. And this is u dot x, and that must be equal to 0. And you see, we are saying that the vectors in W, vectors in R4 with 4 components, satisfying this equation, are simply the vectors whose entries are the solutions to this linear equation. So to find the vectors in W explicitly, we must solve this linear equation. Look at the augmented matrix, and this will be quite easy to solve for, as the matrix is already row reduced. So we can write our solution set. x2, x3, x4 are free variables, so they are parameters. So you can say x2 equals r, x3s, x4t. And if you then solve for x1, you will get x1 is 3x2, so 3r, negative 2x3, negative 2s, negative 4x4, negative 4t. Where again, r, s, and t are arbitrary real numbers. So now we have described our vectors in W explicitly. For any choice of r, s, and t, x1 must be equal to this, x2 this, x3 this, and x4 this. So let's look now at our vector. The vector x, therefore, is equal to x1, 3r minus 2s minus 4t, x2r, x3s, x4t. And as always, to extract from this now that we are looking at the elements of W explicitly, right? For any trace of r, s, and t, this is a vector that solves this equation. Therefore, a vector that is orthogonal to u. Therefore, a vector in the space W. And every time you describe the vectors in your space explicitly, you can always extract the basis by simply separating the parameters. So we are going to split r. Well, there's a 3r here, so it will be 3. There's an r, so it will be 1. There's no r, so it will be 0, 0, plus s times negative 2 in the first entry. There is no s here, so it's s times 0. There is 1s, 1, no s, 0. Finally, we split t, so plus t times negative 4 times t. There's negative 4. There's no t in the second and third components, so it is 0, 0. And finally, 1. So if you look at this, every vector in W must be a linear combination of these three vectors. You see, some multiple r of this vector, call this say v1, plus some other multiple of this vector, say v2, finally plus some other multiple of this vector, say v3. And you see, any vector in W must be some linear combination of the vectors v1, v2, v3. So this proves that the vectors v1, v2, and v3 are generators for the space W. Therefore, the span of the vectors v1, v2, v3 is the entire space W. So we have found generators. So the basis, or at least the guess for now, would be the set containing the generators v1, v2, and v3. But if you remember, a basis must also contain linearly independent vectors. So we must show that these vectors are linearly independent. Well, to prove this, we have to prove that the only way to attain the zero vector through a linear combination of these vectors is with the trivial solution. Therefore, if every coefficient is equal to 0. So let's consider this now. So C1v1 plus C2v2 plus C3v3. So an arbitrary linear combination of these three vectors giving the zero vector. And if we can prove that C1, C2, and C3 are all equal to 0, this will prove that we have a unique solution to this equation, being the trivial solution, which by definition proves that these three vectors are linearly independent. But if you look at this now, if you collapse this combination as a single vector, replacing simply r by c1, s by c2, and t by c3, you will obtain that this vector will be equal to 3c1 minus 2c2 minus 4c3, and then c1, c2, c3. And this equals the zero vector by assumption. So 0, 0, 0, 0. But two vectors can only be equal if they have the same corresponding entries. Look at the second entry of your vector. It is c1, and this is 0. So you see c1 must be 0. Look at the third entry. It is c2, which must also be 0. Look at the fourth entry, which is c3, which also must be 0. And so you see, if you have a linear combination of the vectors v1, v2, v3 giving the zero vector, the three coefficients must be equal to 0. So this equation only has the trivial solution, where every coefficient is 0. Well, this is therefore, by definition, the vectors v1, v2, v3 are linearly independent. And now we have our basis. You see, because the span of v1, v2, v3 is the entire space, v1, v2, v3 are generators for the vector space, and because they are linearly independent, they are also a minimal set of generators. Therefore, we have a basis. The basis contains our three vectors, v1, v2, and v3. So this is a basis of W. And finally, we can ask, well, what is the dimension of W? Right? W is a subspace of R4. The dimension of R4 is equal to 4. But because the basis we found of W contains three vectors, the dimension of W is the size of any basis, the number of elements in our basis, and our basis contains, quite simply, three elements. So W is a three-dimensional subspace of the four-dimensional subspace that is R4. And one last observation. If you notice, when we solved for the elements of our space explicitly, we had three free variables. And as you can see, the dimension of the space is equal to 3. And this is not a coincidence. Every time you find a basis of a vector space, you will first have to solve for the vectors in the space explicitly, and you'll always get a certain number of free variables, of parameters. And you see, to extract the generators, you have to split the free variables, the generators, not the generator, but the parameters. So you see, for each parameter, once you split them, I times something, s times something, t times something, you have a one-to-one correspondence. For each parameter, you extract a generator. And so you'll see the number of generators will always be equal to the number of free variables once you have found the elements of your space explicitly. So always keep this in mind. This will always be the case. The dimension of the space will be the number of free variables of parameters you have once you solve the condition that is required for an element to be in this space. Since we ended up with three free variables, x2, x3, x4, we had three parameters, which gave us each one a generator. Therefore, we have a three-dimensional subspace of R4. Of course, though this is just a heuristic, you have to prove that your generators are indeed linearly independent. But as you can see, in this case, it wasn't that much work, and it's always going to be the case. If you find your generators properly, to prove that they are linearly independent won't require too much work. But always remember, the dimension of the space is the number of generators, and you will always end up with one generator per parameter, per free variable. And so the number of free variables, parameters, will always be the number of linearly independent generators, which will be the dimension of your vector space.